just like in matrices where the multiplication was weird, there's something weird in vectors. It's called the scalar product, sometimes called the dot product, sometimes called the inner product. They can't even decide on what to call it. I like the dot product because you put a little dot in between them. So it's sort of like multiplication, and it's sort of like multiplication of matrices, but instead of multiplying rows by columns, vectors are always columns. But you just multiply the corresponding elements and add them up. So we mainly deal in 2 and 3 dimensions. So this is sort of the extent of our dot product. And this is going to make some very complicated math very nice. But to start off with, all we're going to do is if you write both of these vectors, again, practice by putting the arrows over top of everything that's a vector. So right now, our vectors are written in terms of unit vectors, but I can rewrite V as a column vector, and I can rewrite W as a column vector. And if I did the dot product or scalar product of V and W, all I'm going to do is take the corresponding, so that'll be 2 times 1, plus, these ones are corresponding, -3 times 2, and I will get my dot product to be -4. No problem. So I do find that writing these as column vectors makes your life easier. So this one would be 2, -5, 3, dot product with 4, 1, 7. And again, 2 times 4, that'll be 8. Plus -5 and 1, that'll be -5. And add these together. And you get -24. So again, it seems kind of arbitrary, like someone's making up new rules. Why do we want to do this? Did I make a math mistake? Yes, it is -18. Thank you. There we go. So it seems kind of arbitrary, just like matrix multiplication, until we saw an application of it. Why would we want to do this? So let's look at some of the properties of the scalar product. And in this case, if you do the dot product or the scalar product, because you're multiplying corresponding things and adding them together, the order doesn't matter. U dot V is the same as V dot U. If you have a constant out in front, you could put that constant into one of them, and it wouldn't matter which one you did. You could either do the dot product first and then multiply by whatever this number is out in front. So notice I didn't put a vector symbol because that would just be like a 2 or a 3 or a 7 in front. You could decide to put that number in front with the U or the number in front with the V. And that's the same as sort of your normal multiplication, right? If I got you to multiply 2 times 17 times 5. Your first temptation, well, your first thing you would do is you would do 2 times 17 because you're trained that way, and you do 34, and then you would do 34 times 5 and say, no, Mr. JR, stop, too big numbers, not like you. Okay? Right? But then when you look at it later, you're like, some of you are like, oh, but I could just do 2 times 5 and get 10, and then do 10 times 17 and get 170. That's easier. Perfect. Okay? Same thing is happening here with that. You can change up the order. In the dot product or the scalar product, you could distribute. So notice that you could distribute and do the dot product more if you wanted. However, adding vectors is so easy. So I don't know why there's not very often that you would like, oh, I think I should distribute instead, unless you're doing something theoretical. And there is, in vectors, a zero vector. So you're going to put an arrow over that 0. That is a vector. The 0 vector is the vector of all zeros. Right? And it should make sense if you multiplied every corresponding element with a 0, and then decided to add up all of those zeros, that you should get 0. This isn't bolded because you always get a number when you do the dot product or the scalar product. If you do the dot product of something with itself, you will always get the length of that vector squared. This is actually quite easy to see. Let's say I take a vector that you know the length of. Let's say I take the vector 3, 4, which would be 3 in the x direction, 4 in the y direction. We know that this length is 5 because you could do a squared plus b squared equals c squared and then square root it. Notice that when you do the dot product with the same thing, you get the a squared and you get the b squared. It's just a squared plus b squared, but you never square rooted it. So then you always get c squared as a result, which is the length of your vector, but it hasn't been square rooted. But here is the most important result, that when you do the dot product of 2 vectors, it is equal, the number that you get, this is crazy, because the dot product is so easy to calculate, the number that you get is the length of the one vector times the length of the other vector times cos of the angle in between them. So I have one vector here, u, another vector here, v. I have an angle in between them, theta. And when I do the dot product, the answer that I get happens to be this length times cos of that angle. That seems like it should be way too complicated in a decimal to come out so nice and straightforward. And what this is going to do for us is it's going to make our cosine law that we used to do really, really simple and really amazingly straightforward. Okay? So, first of all, some things that come out of that. If you get that your dot product is 0, just because math isn't happy enough with just one word for things, do you remember the word perpendicular means 90 degrees? Here is your new word for perpendicular. orthogonal. Wow. Someone must have been having a good day when they decided that word. I don't know the history of like, oh, perpendicular is not good enough for you? Let's go with orthogonal. Kind of rhymes with diagonal, but not quite. I don't know. So, because the dot product, right, because your dot product is equal to the length of u times the length of v times cos of 90 degrees. And if you have two vectors, none of those vectors would have a length of 0. They'd actually have a length. If there's an angle between them, they have to have a length. The only way that this side can equal 0 is that if you have a 90 degree there. Because from your unit circle, cos of 90 degrees is 0. So very quickly, you can tell if two vectors are at 90 degrees by just doing their dot product, which again is super simple comparative to what you would have had to do in the past. Now, if the angle between the two vectors is less than 90 degrees, cos of anything less than 90 degrees is positive. And of course, a length is always positive as well. So if the dot product is positive, then you know that the angle between them is between 0 and 90 degrees. But if I had two vectors w and v where the angle between them was more than 90 degrees, you know that cos in quadrant 2, according to your cast rule, is negative. So as soon as your dot product is negative, you would know that the angle between those two vectors is bigger than 90 degrees. And if you rearrange this formula to get cos theta by itself, now we have a quick way to find the angle between two vectors. Okay? Let's think about this prior to vectors. How would you find an angle between two things? If I gave you, let's say, one vector went to the point 3, 2. So this vector I could write as the vector 3, 2. Another vector went to the point 2, 5. I could call this vector 2, 5. Okay? And you definitely can do this using trigonometry you've learned in the past. Can you figure that angle out? What would you have to do? Okay? Well, it makes a triangle. Can you see that if I join this up, I would make a triangle? And I could use my distance formula to find out that the length of this blue line would be the square root of 29. And I could use my distance formula or trigonometry, a squared plus b squared equals c squared, to find the length of this one to be root 13. And I could find this one using a squared plus b squared equals c squared to be the square root of 10. And if you know all three sides, which are all nice square roots, then how would you find theta? You would find theta by using your cosine law. And cosine law, cos of theta is a squared plus b squared minus c squared over 2ab. That's written in one form. You might also remember whichever letter you're using. Do you remember your cosine law? Formulas? Maybe not so much. There's your cosine law formula. So what would I have to do now is I would have to, after doing a squared plus b squared equals c squared, on all three of those, now plug all three of those sides into the formula, I would get a number, and with that number, I could do cos inverse. Okay? Vectors is saying, instead of doing all of that, we still need the lengths, but we could use the dot product instead on the top. You'd have to only find two lengths instead of all three lengths. And really, what the dot product is helping us is simplifying our cosine law. Now, we just drew one out in 2 dimensions. Where this is really nice is imagining things in 3 dimensions. Because it is possible to draw something in 3 dimensions, translate everything back into 2 dimensions, and figure it out. But it's not easy. Okay? Imagine one vector here, one vector here in 3 dimensions. You could take a piece of paper and go, oh, this fits on this piece of paper in 2 dimensions somewhere. No matter where I have these turning in 3 dimensions, there's always going to be one piece of paper that would attach them, and then you'd have to figure that out. Okay? You could do that. It would take a lot of mental space to draw it out in 3 dimensions, first on a piece of paper, and then do a bunch of math to figure out where the 2-dimensional part is, and label all the lengths, and find the angle between. But why would we want to do that when we can do this with vectors? So first of all, I'm going to rewrite V as a column vector. And I'm going to rewrite W as a column vector. And say that cos of theta should equal the dot product of V and W divided by the length of V and the length of W. So remember the dot product? And I'll color code it for you. This will be 12 plus -2 plus 2. And then the length of V, remember that we find our lengths are just a squared plus b squared plus c squared when it's in 3 dimensions. So 9 plus 4 plus 1 square root of 14. And 4 plus 1, or sorry, 16 plus 1 plus 4 square root of 21. And so we have, after simplifying this, that cos of theta is 12 over root 14 times root 21. And we can take out our calculator slowly. Push the button. So first of all, because this is positive, we're going to know that our angle is between 0 and 90 degrees. Right? If you were solving this as a trig question, you would use your cast rule and say it's in quadrant 1 and quadrant 4 because it's positive, and then you would have to write the general solution by going plus 2k pi, where k is an element of all the real numbers. That would give you all the solutions for theta. But we're solving an actual question of an angle between two vectors. When you're measuring an angle between two vectors, okay, this one is B, and this one is W, okay, we are thinking of the angle between these two vectors as this theta here. We are not thinking about this one. This would be the quadrant 4 answer, by the way, going all the way around in the wrong direction. Okay? We're going to actually list it as the, because it's sort of a contextual question, we're going to list it as the acute angle that it is, that angle theta in between them. So now I can go second cos inverse of 12 divided by square root of 14 times the square root of 21. Looks pretty good. And I get theta is 0.7956. That's if I'm in radians. For the most part, we actually will solve these questions in degrees, so you can change your calculator into degrees. If I type this in again in degrees, it would tell me that theta is 45.58 degrees. So we found really quite easily, even though this is in 3 dimensions somewhere, what the angle is between those two vectors. This is really, really important for working in 3 dimensions. And it makes the math way easier than doing the math that we would have had to do with the sine law, cosine law, and making it fit in 2 dimensions. Remember that orthogonal means 90 degrees. So make some sort of statement that you understand that if it's 90 degrees, then cos of 90 degrees would be 0, and the dot product is 0. So if I take one vector, which is 2m, m, and k, and I do the dot product with the other vector, which is 1, 3m, oh, not k, sorry. This will just be an 8 and -1. It has to equal 0. Again, how does the dot product work? Multiply those ones together. This will be 2m plus, multiply these ones together, 3m squared. Multiply those ones together, -8. And that has to equal 0. So we need to solve for m. It's a quadratic. Maybe we can factor. If we can't factor, we'd have to use the quadratic formula. If I could factor, this would be 3m and m. The last numbers have to give me -8. I'm liking 4 and 2 because it would make 6 and 4. 6 and 4 makes 2 if the 6 is positive and the 4 is negative. So m would equal 4/3, or m would equal -2. Did they ever use the word orthogonal in physics? No. This is the first time. New word for the day. So exciting. When I lived in South America, I always tried to have a new Spanish word for the day that I would try to learn. Now when I watch Spanish movies, I seem to be only learning new swears. I don't know if that's a good thing or a bad thing. Again, life is easier using our column vectors. Something is parallel if it goes in the same direction. If you wanted something parallel, you could take the vector that we have and multiply it by anything in front. So to start off, I'll just say k. You could pick 2. So for example, if k equals 2, 8, -6 would be parallel. Even if k was -3, doesn't matter positive or negative, k could be anything. K even could be pi. You could grab 4 pi, -3 pi if you really wanted to mess things up or use decimals, any number, because what that value of k in front will do is just going to make your vector longer or shorter, and sometimes change its direction, but it will still be parallel. But this idea is the idea for parallel with vectors. Okay? Don't need to use a dot product or anything for parallel. All we have to do is say that it's some multiple, any 2 vectors that are multiples of each other will be parallel. When you think about vectors, okay, and you think about when you've done parallel and perpendicular and stuff before, you've always done parallel with slopes. Okay? Can you see that writing as a column vector the slope of this one is -3/4? Why is it -3/4? Well, slope is rise over run. Your rise is your y value. Your run is your x value. So a column vector is kind of a slope, but just flipped on you, because it always has the x on top and the y on the bottom, but slope is always y on top and x on the bottom. Can you see that when I multiplied this by 2, the slope of this one would be -6/8? And of course, that fraction would reduce to the same thing. If you want to make something not parallel to you, you just need to make sure it has a different slope. The easiest way to do that is just to change one of the numbers, right? If I keep the 4 the same, but I make this anything, can you see that its slope would be 7/4? Is it the same as what we started with? Obviously not. As soon as I change just one of the numbers, right? You could, like, if you like to live on the edge, pick two random big numbers. Chances are very slim that they reduce perfectly to be the 4 and the 3. Right? But you're playing a little bit. If you're just doing a random, there is a chance that you could, very, very small chance, but possible that you could screw up and pick something that's parallel. But this is very easy. Now, if you want to pick something orthogonal, well, we could think about the dot product, because if I pick orthogonal, the dot product would have to equal 0. But the mathematics gets a little bit tricky there because you have, here's u, 4, -3. I don't know what my x and y are, but I'm going to make a dot product, and I need it to equal 0. The problem is that creates the following equation, that 4x minus 3y has to equal 0, and I have two variables but only one equation. You could do some guessing and checking. There's many answers that work for this. In fact, you could plug in anything for x and solve for y, and you would be right, because there's infinite amount of answers. Okay? However, if we know that the slope of this one was -3/4, what do we need the slope of this one to be if they're perpendicular? The negative reciprocal, in which case it'd be 4/3. So one possibility could be to write the vector 3, 4. Right? Another possibility is to use this equation, pick a random number for x. 9. If x is 9, you would have 36 is equal to 3y. Y would have to equal 12. So another possible answer to this question would be 9/12. Can you see that Rohan's answer is parallel to the answer that we got by just using the negative reciprocal? 9/12 is just 3/4 times by 3. And of course, if it's parallel to the answer, both of them will be perpendicular or orthogonal to the original. So you can use the dot product and just choose any value for x. Thank you for choosing an x value that didn't result in fractions. But it's not wrong if you did get a fraction. But you can also use the idea of slopes here to think about parallel and perpendicular. So here's that idea that I talked about before for parallel that's really going to help you with this question. If they're parallel, then 1 and -3 and 2 and x have to be related that one is a multiple of the other. So I have a choice. I can say, I can put the k here or the k there. And it doesn't matter, other than I sometimes like to put the k in the place where I can do the mental math the easiest. I kind of like the k on the left here. How hard is it for you to figure out what k is. In other words, according to this, k times 1 has to equal 2. You can probably even just look at it and say if it needs to be 2, this has to be a 2 out in front. That k has to equal 2. And if k is equal to 2, well then x would have to be negative 6 if they're equal. And in these questions, this is probably one where the dot product equaling 0 is probably a really nice way to think about this. So if they're perpendicular, I know that if I take the dot product of these, oh, and it's very important that you make it with a dot, because with vectors, there's 2 kinds of multiplication. You know how you learned, oh, you can write multiplication, like in elementary school, how did you write multiplication? With a little x, right? That's a different kind of multiplication in vectors. There's a multiplication with an x and a multiplication with a dot. We call one the dot product, the other one the cross product, because the x cut makes a cross. So we're going to learn that next. But we can use the dot product here because we know this has to equal 0. And so if we multiply these, this will be 2 minus 3x has to equal 0. So solving for this, 2 is equal to 3x. And x would have to equal 2/3. If you wanted to, I find this a little bit more abstract, but you could use the slopes. The slope of this one is x over 2. And it would have to equal the negative reciprocal of this slope. And the slope of this one is negative 3 over 1, so the negative reciprocal would be 1 over 3. And then you can solve for x. I just find that with using slopes, and you've got having to, first of all, think of the slope as the flip already, and then you're supposed to flip one and flip it again to get the negative reciprocal and make it negative, is a lot of flipping in your brain. And I find the more things you flip in your brain, the more it gets dizzy and chances of making a mistake. So I think in this situation, the dot product is a lot easier. So there's our dot product. Tomorrow we're going to learn about the other multiplication, the cross product. But I've got questions for you to work on. Homework for tonight. Up till now, I think the vectors homework has been, I would say, relatively straightforward. This is an important one, the dot product, the scalar product, so make sure you're working on this tonight. And you can start doing a couple of them. I still got about 5